Well, hi everyone, and welcome back to part 9 of the Block 74 Apollo Guidance Computer project that I'm working on. Today we're going to talk a bit about the L register, but before we get into that, I'm actually going to go back and look at the Q register a little bit more. So first, I want to thank Mike Stewart, who helped point me in the right direction when it came to understanding a little bit more how the I/O channel logic works. In a couple episodes before, we talked about the Q register and how it's one of the registers that also um, provides an interface into some of the I/O channels, and those are the channels that talk to the actual hardware on the spacecraft itself. Now, when we went through the Q register, one of the or at least what I thought at the time, was that the Q register or that the I/O bus or the channel bus was kind of a separate bus from the write lines. So here we have kind of our write line, um, bus, which is how data kind of flows into these registers and out of these registers. And I was kind of thinking that the I/O, so these kind of in-out channel word, was kind of a separate bus that managed the data flow between the Q register and the L register, which are the two registers that kind of have some of the same behavior, and that those were used to actually bring data in and out from the channel bus into the rest of the computer. Now, part of the reason I thought that is if you go into some of the documentation, it talks about these I/O channel write lines. But it turns out that that's just more of how it refers to some of the data lines coming in and out of those I/O channels um, as some of the channel logic. And in fact, the way that those I/O channels work is that they place data onto the write line bus or read data off the write line bus into the appropriate I/O channel registers, which means that the Q register and the L register, rather than being registers that kind of act as that bridge between the channel bus and the I/O bus and the um, write line bus, is that these are two registers that actually can be treated as a channel register or as a internal central register in the AGC itself. So that actually made me have to go back a little bit and slightly adjust the Q register. And why this is important is because it's the same kind of design change that I had to make the L register so that it would work as well. So before we get into the L register, I'll just kind of go back and talk a little bit about what I had to change on the Q register. So you can see here, I kind of had to strike out the CH IO channel bus because it actually doesn't exist. It's all write lines on the internal data bus. And so when you read the instructions of kind of how it works, you kind of see that there's this channel instruction write signal, which is the XTO, which in this case the address, or what the address, or the timer to kind of bring it in, or XB2, so memory address 2. That's how we can address the Q register both as a directly addressable special register. We can also access it using the WQ and RQ pulses, but we can also use this to apply channel instructions against the Q register as if it were another IO register. And that's kind of the what I figured out the other night to say, oh, okay, this is a bit different than what I had originally thought. So I'm just going to just flip and bring up the circuit diagram for the Q register and kind of how this changes things, because it actually makes the Q register quite a bit simpler than what it was before. So a few things that have changed. One is that the sort of the WCH and the RCH, which are the write channel and the read channel control pulses, are now we're just kind of NORing them together with XB2 to determine whether we should be writing data into the queue register, or in the case of an RCH, whether we should be reading data out of the queue register. And so this kind of simplifies a lot of this logic. And before, if you remember, we actually had a whole bunch of 2-to-1 selectors where we would, originally saying, okay, well, depending on the WCH control pulse, we would determine, do we write in data from the write lines, or do we write data in from the channel bus? But again, the channel bus doesn't exist. It's all write line bus. So it's just another mechanism that allows us to write data into the queue register from the write lines. So that means we're able to get rid of those 2-to-1 selectors. So there were 4 of them, because each one is a quad 2-to-1 selector. And we're able to kind of just bring in the write line data directly into our registers. And then on the output side, again, we just read the data out onto the bus using our octal transceivers. Now, before, we actually had 2 sets of octal transceivers, one that we would use to write data out onto the write line bus, and then another set to write data out onto the channel bus. But again, channel bus doesn't exist. So again, this really simplifies things, and it just means the write channel, RCH, is just another kind of mode that we can use in order to write data out of the queue register and onto the bus. And like I said, this is so that some of the instructions, the machine instructions that are applied to the I/O channels, can be applied. So basically, the queue register becomes a valid source and destination for those channel instructions. So as a result, like I said, that makes it quite a bit simpler on the queue register. We actually removed 6 chips, and the logic was simplified a little bit as well. So if we go back, that means our bill of materials has kind of been updated. So this is our queue register redux. And I mean, that's one of the reasons why I'm doing this project is, I want to learn and kind of figure out the Apollo guidance computer as I build and design it. So there's going to be cases where we're going to have to go back, revisit, update, change. And as I get closer and closer to the end of the project, I'll start publishing more of the schematics, so that if folks want to actually build their own, at least they're going to be building off of something that's a bit more kind of tested, thought through, and validated. Now, on to the L register. So the L register is kind of the counterpart of the A register that we talked about in the last video. So when it comes to mathematical computations within the Apollo guidance computer, there is the accumulator, which is the kind of, where most kind of the outputs of math operations are stored. But whenever you need to do a double precision mathematical operation, we have the L register, which is the low order product. So if we're doing multiplications, or basically math where we need more than the 14 to 15 bits of precision that can be stored in the accumulator, we can also store some of that data in the L register. So it kind of shares a little bit of similarities with the A register, and some similarities with the Q register. So if we look at kind of the description of how the L register works, there are a couple ways that we can write data into the L register. So one is we get the WL control pulse. So that's kind of the more normal way, where we would just look at, okay, if we get a WL, and on the right timer, we'll load whatever's on the write lines into the bus. The L register is also a special, directly addressable register at 001. So that's if we use that WSC and RSC control pulses, we can do that with, this should be XB1, which is memory address 1. Um, but we can also use the WCH and RCH to basically make this look like channel address 0, 1. So similar to the Q register, we can apply channel instructions against this register as if it were an IO channel. Now, there's another kind of scenario around what data can be written into the L register, and this is used during multiply. So this is kind of the counterpart to the WALS, WALS control pulse that we talked about when we went through the A register. There's a kind of its counterpart, the G2LS control pulse, and that writes again, a shifted version of data into the L register. So when we talked about the A register, basically all the write lines are kind of shifted to um, kind of bits or to the left as a multiplication. And so what we can see is, well, some of those write line 1 and 2 that weren't in the A register once we did the shift now show up within the L bit. So we can see bit 13 and 14. And then we also have a bunch of data that comes in from the G register, which is basically the memory register. So it's basically used to facilitate transfers to and from memory. Um, so at least two in the case of the read write memory, so the RAM, and then from when it comes to ROM or the read only or basically the control instructions. So the G register is going to be kind of that intermediate point of where when we request data from memory, it's going to sit within the G register and then be passed out to where it needs to go. And if we need to load data into memory, at least for the rewritable memory, we'll push data into the G register and it'll move from there. So that'll be one the G register will cover in a subsequent episode because it is a bit more complicated in kind of the what it does and how it can be used in order to transfer data to and from not only the write lines but also in some cases to various registers directly. So we'll flip back to the schematic and kind of look at how the L register looks in the schematic. So we have the L register, and this is the control logic, and this is now very similar to the control logic that was in the Q register. The only difference is instead of XB2, we have XB1, so we can generate our write line control, or basically the control pulse to write data into the L register from either the WL pulse, the memory address 1 with a WSC. So if we're writing it in as a special directly addressable register, or WCH if we're writing it in as a channel register. And then this will generate our control pulse in order to write data into our D register. So these are our registers right here. And then we have basically the write logic in order to determine when do we push data out onto the bus. And again, similar logic. We have the RL pulse, we have the RSC, and the RCH, and these two basically are also combined with XB1. Now, the one nice thing about the L register is that going through some of those control pulse combinations that we talked about in the last episode that can result in bus contention is that there is none that the L register has to deal with. Now there are a few more that again I really appreciate Mike Stewart kind of pointing out that there were a few that I missed where there are cases where data is ORed onto the write line bus. So some of the scenarios where we will write constants onto the write line bus, and that'll be something we'll talk about in a later episode. Some of those constants are just written directly, so we'll load a specific value onto the write line bus, and some of them are actually just ORed with whatever the contents are onto the write line bus. And this is something I'm learning a little bit more about as I go through is kind of how these functions work when it comes to providing data onto the write line bus. which means I actually had to make a slight change to my A register that we talked about last week, in that uh, when we went through the A register, there were some specific logical operations we were talking about. So with the mask instruction, we were kind of looking to AND data, and then there was a exclusive OR logical function that we are looking to do the exclusive OR. Now, um, as you go through and you look at the sequence of control pulses um, that make up that instruction, the computer actually does the appropriate logical operations and inversions um, to generate either that AND or exclusive OR, only using OR on the actual write lines. So some of the logic that we worked on last time actually was able to simplify quite a bit, because if I, and I'll just maybe flip over to the A register so we can look at it briefly, is, we have here these kind of ALUs where I was saying, okay, we have to either do our AND logic or we have to do our exclusive OR logic. But the reality is that all this has to do is the OR logic. So I may actually not need to use these ALU chips on some of the other register boards, such as the X register, because that's where we're going to have to handle some of these other scenarios, as well as on the bus register and a few other scenarios that we're working through, because we don't have to sometimes do an AND, or sometimes do an OR, sometimes do an exclusive OR. The control pulses and the designers of the AGC were smart enough to basically decompose all of that into OR logic, so that we'll see which is simpler from a number of chips, just so that everything can fit on the board. But it does, again, make things a bit simpler. Okay, back to the L register. So what we have here is we have the two kind of selectors, and again, this has been simplified because there are only two cases. Either we load data directly in off of the write line, so WL01, LO2, 3, and so forth, or we load the contents of the G register, and then we have our write line 1 and 2 here, depending on if we are executing that G2LS control pulse. So we just bring that once, if this is asserted, which means it goes 0, we invert that to a 1. And if it's been asserted, then we basically pick the second set of inputs in order to load into our register. Otherwise, we will just load things directly off the write bus. And then on the read side, where we push data back out onto the bus, it's just, again, our two octal transceivers, which push the data out. Now, there's one other kind of function I'm going to add to the L board, and that's just to, as you start realizing, how do I fit all of the kind of the logic and the control instructions together? You start trying to figure, okay, well, the backplane connectors I'm using has 96 pins, and unfortunately, if you start adding all the different write lines for the different registers and the control pulses, you easily get well over 100, probably 150, 160 different potential connectors. So how do I start economizing the best way of using those 96 pins? And then in some cases where I'm going to have to connect directly between different registers, using different jumpers or connectors to just connect those registers together. Because in this case, so the L register, we have not only our write lines, which we can grab off that 96 pin kind of common backplane, but I also need to provide the contents of the G register. So that's where we're going to use a jumper to basically bring in the contents of the G register so that we can select between one or the other when we load our L register. And there's actually a kind of reverse control pulse, which loads data from the L register into the G register. So we'll also have to have kind of a jumper that'll bring the L register or make the L register contents accessible to the G register. Now that means that we have the contents of the G register available on this board for the L register. And as I've been designing the G register, as I mentioned, it's fairly complicated. And I'm starting to run into challenges of being able to fit all the chips that I'm going to need onto that G register board. So one thing I'm going to do is, when I go to order my second batch of boards for the registers, so kind of those little compute boards that we talked about in the hardware video, I'm actually going to make it a little bit bigger so I can fit more chips on it. So I'll kind of have a short board and a long board to add some of those you know additional chips for the more complex cards. But one of the tests, and we'll talk about that in a subsequent video, is that they're in order to do kind of the branching logic, and we've talked a little bit about this. There are a number of kind of test control pulses where the control pulse will be, test the contents of, the what's on the right bus. Is the information on the right bus even or odd or negative? And one of them is a test to see if is the contents of G 0. So what I'm going to do is I'm actually going to, because I have G on this board, is I've just created a little bit of a logic tree that'll basically do the test to say, is G 0? And then I can use this for some of the test logic so that on the test board, I can basically just do if I get the control pulse that says, are we checking to see if G is 0? Then we will, this kind of logic will be available on the backplane for us to be able to validate that test. And then depending on the results of that test, that information is, we basically set the branch registers one way or the other, and that branch register is used when we actually do our instruction decode as to what control pulses we actually need to set. This provides our conditional capability in the computer. So this is just, again, because I've got space, and the L register doesn't use up the full board space, so I'm just going to add this logic here. And in this case, I'm just adding you can see there's a 5 volts. Like, well, why didn't I just use a 2-put AND gate? And it's because the 74LS11 actually has three input AND gates on it. So I'm just be able to save adding another chip. I believe it's the 74LS08, which is a quad 2-input AND gate. So this just basically saves us from having to add another chip and allows us to use the third 3-input AND gate that we have on this chip. I've just kind of simulated the functionality of that of this kind of test here, so you can kind of see if everything is 0. We're going to basically send our pulse, and then otherwise we are not. Coming back to kind of what that looks like from a bill of materials for our L register, and I haven't built it yet, so this is just a picture of the Q register, but it's going to look fairly similar when it's done. Is we're going to have our 4-bit D-type register, so that's actually where we store the data itself. We'll have the 2 octal transceivers to push data out onto the bus. We'll have 4 dual 4-line 2-to-1 selectors. This allows us to either do that shift operation if we're doing a multiplication, or just load the data in directly off the right lines. And then this is our control logic. So we've got 1 hex inverter, a quad 2-input NOR gate, and then a try 3-input NOR gate. So again, thankfully understanding that channel bus logic has kind of simplified things quite a bit. So again, thanks for joining. Next episode, we're going to start getting into a couple of the operand registers. So we'll probably that'll be probably one video that would, if we covered it all, it'd be pretty long. So we'll probably start talking about the Y register, which is one of the 2 operands, and then we'll talk about the X register, which is the second of the 2 operands, and then the 2 of them together, work with the adder to actually perform the mathematical functions itself. So that's something we'll start getting into in the next episode. But otherwise, if you like what you see, subscribe. I try to publish a video probably every week or so as we go through this. And as always love the feedback. And thanks to people that are providing feedback and asking questions. And pointing out errors, because this is a kind of learning journey, as I said before. And so if you see something, say something so that I can address the error, fix it, and share that information back with everyone else. Anyways, have a great rest of the week, and we'll talk to you in about a week and a half. Thank you, everyone.